Okay, so hopefully this is recording. If you're absent and having to watch this, this is the video on waves. So again, a wave is the motion of a disturbance. There are internal forces that exist between the particles of a medium that allow the energy of that disturbance to travel. So the only way that I can get energy to flow through that medium is because of those internal forces. Your chemistry class might call those intermolecular forces. There's one one particle that's attracted to the next particle through some of those internal forces or intermolecular forces, and we allow that energy then to transmit through that medium. Disturbance travels in a straight line. So I want you to look at this disturbance here. So my hand is creating disturbance left and right. I put an alligator clip sort of in the middle of this slinky so you can see how the particles themselves move. So that alligator clip is connected to the bottom of that slinky, and I want you to look at its motion as the wave moves through it. And if you were to describe that motion, you would say it looks like it's oscillating. That alligator clip is not moving along with the wave. It stays where it is. It just oscillates. What kind of motion would you describe that oscillation as? Simple harmonic. So the wave travels in a straight line. The particles oscillate about their equilibrium position. And in that motion described as simple harmonic. So my goal yesterday was to help you understand that simple harmonic motion is related to wave motion. That particle there is oscillating. As the energy flows through it, it oscillates in SHM, and that allows the energy to transmit. Waves require no bulk transfer of matter. I'm not moving matter between me and Nathan. If I'm going to send information to you, I might just send it as a wave, and I'm not moving matter from you to me. I'm moving energy from you to me. What that means is that I can transfer it very efficiently. I get a very efficient transfer of energy. It doesn't take much. If you notice how little my hand has to go through its motion for me to be able to transmit that energy to you. If I took a ball and tried to throw that using the same amount of energy, it wouldn't go anywhere, right? So I'm able to get the energy to transmit great distances because of the efficiency. We can travel, we can make information travel great distances with very little energy needs. Now, the rest, I'm going to show you a simulation here from the other guy I showed you, the video I showed you of the guy with the long hair. He's like a colleague of mine, contemporary, like high school teacher. The guy I'm going to show you here is more of a college level, graduate level, PhD level person. So this is Dr. Dan Russell. I've been following his page for a long time. So he used to be at Kettering University, formerly GMI, General Motors Institute. He's now at Penn State. And I've been following his thing for a long time. Here's a wave. Now you've probably seen a person wave before if you've ever been to a athletic kind of game and someone started a wave, something like this. It sort of transmits from one person to the next and it goes around. Now, if you haven't seen that, that's okay. This is what it would look like if it were just a red bar that's pushing on the particles that's next to it. You notice that as the red bar pushes on the adjacent particles, those particles push on the next particle, and then it just transmits that energy. The question is why don't those particles just move along all the way through there? Why do they just sort of go like that and then come back? What is it that causes them to go back? Thank you, Nathan. Yeah, they're in an equilibrium position. When I displace it, the adjacent particle, if it pushes it forward on the adjacent particle, what does the particle do? It pushes back. So it just pushes it right back to where it was. I'm able to transmit the energy through that medium because of internal forces. Now that's a pulse wave. This is more of a continuous wave, and this is important for you to understand the difference between how a particle moves and how a wave moves. The particles make up the medium. They're oscillating. The wave is an energy wave that travels from point A to point B. One thing could be described as a constant speed, right? That's the wave motion. The other is described as a simple harmonic motion where its speed is never constant. It's constantly changing. So that's a demonstration to sort of show you how energy can transmit through a medium as a wave. Now, there's other things in here. This guy has all sorts of things that he's put together because he works in a PhD level program in acoustics. And so some people that are interested in going into that kind of field, you would study this in much greater detail. Here's wave motion in space and time. Sometimes the links are slow, especially when I have a recording going on here. In your math classes, you study sines and cosines and business like that. This one is going to show you sort of how that's, again, related to simple harmonic motion, if it works. Okay. Now, you probably have seen this notation before. Is this correct? Have you guys seen waves written in your math classes as like some sort of wave with, y is equal to 3 sine of x or something like that? You guys have done that in your math classes, right? So this thing is just saying that this is a function of x and time. A represents the amplitude. Omega represents something like a oscillation frequency. T represents your time. Kx is just a phase shift, but that's just a mathematical notation. This is what it would look like if I were sending that wave along this medium. And so again, these visuals hopefully help you make a connection between what we study in physics and what you've done in math. That red particle could represent a portion of a medium. The disturbance travels through that medium and it causes that thing to oscillate like a mass on a spring. Okay, so that's again just showing you how the physics of that is connected to the math of that. Now, there's other things. I'm not going to show you superposition yet. We're going to start looking at what waves can do that particles can't. We'll look at that. Fourier decomposition. All these things are really cool to see. I want to show you really quick something called longitudinal versus transverse. And so, let's see. Okay, so this is technically what's called a longitudinal wave. The particles move in a parallel fashion to the way the wave is moving, so that's longitudinal. Here's a transverse wave. And so transverse waves, the particles move up and down as the wave moves left to right. I could demonstrate that up here. Here's transverse. Let that dampen for a second. And here's longitudinal. So longitudinal would look more like this. And so you can probably see from a side view that you can see the particles sort of oscillating. It's really hard to get a really good longitudinal wave up there, but that's how that would work. Now, you guys live near Lake Michigan, and you've probably been out on some water waves before, so I want to take a moment and let you look at what surface waves would be on like Lake Michigan, could be in an ocean as well. You notice that it's really a combination, that the surface itself goes through a combination of transverse and parallel motion. So transverse and longitudinal. And if you've ever ridden on some waves on the top, sometimes you feel like you're pushed towards shore, and then as the wave passes, you feel like you're sucked back a little bit. And so that's evidence of the motion of the particles being more circular. Now you dive down underwater 3 or 4 feet. Can you still feel the wave pass over top? To some degree. You might notice that there's still energy of oscillation in the waves that are, and the particles that are down lower. It's certainly lower amplitude, but you can feel it. Okay, so notice that I got circular motion there. So it's a combination of transverse and longitudinal. Raise your hand. You ever been in a lake like that and you've ever felt like water going over top of you? Waves? Okay, only a few people. Let the record show only a few. All right, now if you've ever been in an earthquake. If you've ever been in an earthquake, these are called Rayleigh surface waves, and I want you to pay particular attention to the way the particles move. First, they're no longer circular. They look more elliptical. And if you look really closely, you might be able to see that there's a different direction for the waves on the crust or on the surface versus those that are down below the surface. Can you see that one side is circular or anti-clockwise and the other way is clockwise? That produces a shearing effect, right? So as I go down below their surface a little bit, you're going to see sort of a shearing effect. And sometimes when people are looking at earthquakes and plate tectonic shifting and stuff like that, that's that shearing that can take place. So that right there is, again, different kinds of waves. You notice that all of these things are vibrations and they transmit through, in this case, the Earth's crust. Okay. Now, there are other things here that I wanted to show you. Here's phase displacement between velocity and pressure for a longitudinal sine wave. I was attempting to show this to you yesterday, talking about phase shifts. If you've been up far along in math, then phase shifting is something that's in your area of expertise. If you haven't seen it yet, this might help you a little bit if it loads. Okay. Phase between displacement, velocity, and pressure for longitudinal sine waves. Now I'm going to let this one stay up here for a minute while you look at it. Maybe you could hit the lights for me over there. I know you can't see it really well from the distance that you're away. So the top wave, the black wave there, is displacement. The one below that, the red wave, is particle velocity. And then the pressure, the blue one, is a pressure wave. So these are longitudinal in nature. So these particles are vibrating left and right like this as the wave moves between it. Now, I want to talk about phase relationships. To really truly understand waves and how they work and interference patterns and all that kind of stuff, you have to understand phase. So I'm going to stop this thing. I can't stop it here. I don't have that control. So what I'm going to do is I'm going to stop it on this screen up here. Now, for the video recording, I don't think it's going to work. I'm just going to try to stop it at a maximum positive displacement right there. It's pretty close. So it's still moving on this, but it's frozen up there. Do you notice that when the displacement is at a maximum, what's the particle velocity at? It's at 0. Just like we saw with the mass on a spring. That when it's at its maximum displacement, either up or down, it's not moving. Now in this case, the pressure is in phase with the particle velocity. And we would say that the displacement is 90 degrees behind the wave velocity. It's out of phase by 90 degrees. In your math classes, you might call that pi halves, whatever. It's a phase relationship. So again, that shows that there with that longitudinal wave traveling through that medium. Now I'm going to show you some other things. Let's see. Displacement, don't need to look at that standing. Let's look at this one over here. I know we have some tennis players. We have some soccer. Let's see, some baseball bat players and stuff like that. Let's look on the baseball bat for a minute. So there are modes of vibration for all of these objects. Without seeing the coupled pendulum thing that I was going to try to show you yesterday that wasn't working really well. These things are interconnected with bats are interconnected with all sorts of internal forces. And everything's made up of atoms, and those atoms are just like masses on springs that are connected to one thing through another through intermolecular forces. A bending mode could look like that. We could have a second bending mode, a third bending mode, and then a fourth. These are all different vibrational modes that these things can go through. If you've ever hit a ball with a bat, you know that there's a sweet spot. That sweet spot, it occurs in one of those black dots that you see up there. Those black dots, you notice they're not moving at all. Those are technically called nodal locations for that. But these things are vibrational objects, and the way that they're vibrating has to do with those different modes that I was attempting to show yesterday. Okay, so that's something that would play into any kind of sport in which you have something that you might be hitting with something else and you want to get good effective energy transfer. All right, there's a lot more than we have time for. If you want to find this source out there, you just type in acoustics and vibration animations. You could probably spend an hour looking at all the various simulations. I don't have time for that, but if you'd like to do that, it's there for you. All right, we need to look at this thing called wave speed. Lights off or on? Off. All right. Now, you have seen a representation of a wave before. I'm sure you have. If you haven't seen it, then this might be new to you, but I think for many people this is a review. That is an amplitude. So the amplitude is a maximum displacement from equilibrium. This portion is a crest. This portion is a crest. These are troughs, right? So the bottom points are troughs. Maximum points are crests. The distance between a crest and a crest is what's called a wavelength. The symbol that we use, I know you guys can't see it really well, is lambda. Lambda represents a wave length. And I don't think in your math classes, I don't think you guys use the symbol lambda to represent that. Do you or no? I don't know. Math classes? Sorry. So that is it's a Greek letter, lambda, looks like an upside down Y. It's a symbol we use to describe the length of a wave. The repeat distance. Now, a frequency and period, we defined those before. Wave velocity, I want to take a moment. If I were to ask you to measure the wave speed for a pulse, it'd be fairly simple. Would you agree? Nathan, you're 8 meters distant from me. It takes about 2 seconds for that pulse to travel from you to I. If you're 8 meters distant and it takes 2 seconds to travel this distance, you could tell me the speed of that pulse. It's 4 meters per second. After 1 second, it travels 4 meters, and the next second, it travels another 4 meters. That would be the wave speed. It's harder if it's a continuous wave, because a continuous wave, it's not like I can just see one pulse that's moving. It's much harder to do. And so I want to show you how we could calculate that. For those of you that are runners, you might understand that the stride length is very similar to a wavelength. So when you walk through that sand, your footprints leave sort of a repetitive pattern, and you could say that the stride length is most similar to a wavelength. So stride length is like a wavelength. This could be your right foot, that's your left foot, that's your right foot, that's your left foot, and the distance between those could be your stride. Now, if you're a runner, you might also understand something called cadence. There's an optimum cadence for runners that are endurance runners, about 180 steps per minute. Are you familiar with that number? About 180. Now, cadence is pretty similar to a period idea, right? So cadence is sort of like a period. For some reason, it locked up on me. Cadence is similar to period. The symbol that we use for that is T. If I wanted to find the speed, I would take a distance over a time. Well, the distance would be a wavelength. The time would be a period. So how far a wave travels in one period is a wavelength. So I could say velocity is equal to wavelength divided by period. And because period and frequency are related, see if I can write on the board again. Because frequency and period are related through this equation, I could say that the velocity of a wave is equal to its wavelength multiplied by its frequency. And so I would imagine in your chemistry class, when Mr. Newton had out his, it's called a Rubens tube, pipe with gas and lights music on fire and all that kind of stuff. It's pretty cool. What he's trying to show with that is that wavelength and frequencies are inversely related. If you increase the wavelength, you decrease the frequency and vice versa. There's a lot more to that. And I think he even said that, oh, wait till you take physics and you'll see some of that more. There's much more to that demonstration than just wavelength is frequency times wavelength. Or velocity is frequency times wavelength. You have seen that equation, correct, if you've been in a chemistry class? Okay. Now, the motion of the particles in a wave can either be perpendicular, which would be a transverse wave, or they would be longitudinal, or parallel, which would be a longitudinal. So which way the particles move depends on what kind of wave we have. Mechanical waves require a medium. That medium provides a restoring force. In order for something to be able to transmit through it, there's got to be a restoring force. That force comes from the intermolecular forces of that medium. Electromagnetic waves, those are things like light, radio waves, X-rays, things like that, do not require a medium. And the reason for that has to do with something called the electromagnetic force. We'll study that in Unit 5, which is on electricity and magnetism. So EM waves do not require a medium, because the restoring force has to do with electromagnetic interactions. So we'll show you that stuff in a later unit. Okay. Now, wave speed depends mostly on the properties of the medium and the type of the wave. I want to focus in on the medium properties so that I can write on the board. I'm going to turn this off and turn this back on. So please give me a moment while that thing is doing that. For some reason, it just shuts down on me. It's probably because of those simulations. If you're at home watching this video because you're missing class today, I don't know if the screen has gone blank for you. It's blank for the. Okay, so wave speed. Mechanical waves depend on mostly on the medium and the type of the wave. Now, I would imagine in your chemistry class, you guys had to have talked about different states of matter, correct? Solids, liquids, and gases. Is it possible that you could, you're going to go on record here because I'm recording this, is it possible that you could tell me what makes a solid a solid? What is it about a solid? What are its features that make it a solid? Would you be willing to go on record? Tell me what it is. What makes a solid different than a liquid? Thank you. You must be taking chemistry right now. Other people are like, no, I don't want to talk about that because I took that last year. What makes a solid different than a liquid?
How close the proximity
Say it one more time, Nisma.
How close and constant these molecules are.
Okay, so one thing, and thank you, Xavier's got it, how close the particles are together. Solids are really close together. What's another thing?
The particles can vibrate.
They always are vibrating, so something you guys should realize that particles are always in constant motion. Absolute zero would be the temperature at which motion ceases, and that's sort of a theoretical minimum. If you guys are familiar with that, right? Okay, what's up? Something else?
They have a really strong molecular force.
Yeah. So solids themselves are characterized by particles that are really close together. So the particle spacing is something that plays a role. Come on, give me that particle. Okay. The spacing of particles is important. Solids have really close particles, and they are very strongly interconnected. So you could expect that mechanical waves will transmit pretty quickly through solids because particles are really close and they are really strongly connected. Now, there's other factors that come into play. The mass of the particles can affect the speed at which the energy transmits. And I want to take for a second different kinds of gases. We normally listen to sound through air. But if you listen to sound through helium, it sounds quite a bit different, right? You may have seen people that inhale helium from a balloon and then talk and their voice goes really high pitched. That's because the mass of the helium is different than the mass of the air particles. So mass affects it. Speed, and thank you, Gabby, for talking about vibrating objects. I mean, solids vibrate, so do liquid, so do water molecules, so do gas particles. They have to be sort of in some sort of constant motion. But the speed at which particles move through SHM is related very strongly to temperature, especially for gases. So because gases have particles that are so far apart, the warmer the temperature, the higher the temperature, the faster those particles are moving, we can transmit energy more quickly through there as well. Now, something that I don't know if you guys get in your chemistry class, because I know you use the equation for this, but I don't know that you understand the underlying physics of that coming from chemistry. So I want to take a moment and talk about this relationship. If speed is constant, and the purpose of that Rubens tube is to show you what happens when the speed is constant, doubling the frequency will have the wavelength. What that means is that these two things are inversely related. There's an inverse relationship if speed is the same. Now I'm going to write that out without numbers. I'm going to write that as an equation with letters. If the speed is a constant value, and it depends on the properties of the medium. The medium doesn't change, but I'm going to change the frequency. Then what that means is if I have a high frequency wave, if F becomes bigger, then the product of those have to be the same. That would mean the wavelength would have to become smaller. So when Mr. Newton played the music for you, or did he have a tone generator to be able to play like a 500 hertz sound or a 1000 hertz sound and stuff? Or was it just music? Okay. Regardless, if I make the frequency higher, that should make the wavelength smaller if the speed is a constant. What if I make the frequency lower? That should make the wavelength larger. So that represents what we call an inverse relationship. One goes up, the other goes down. Demonstration. Here is a low frequency wave. The speed at which that wave propagates depends on the medium properties. I increase the frequency, and you notice that the wavelength decreases. You can see that. There is a dependence, inverse dependence on those things. Okay. Now we're gonna do a few problems. A fisherman noticed the wave crest passed the bow of his boat. Every 3 seconds, he measures the distance between the two crests to be 6.5 meters. How fast are the waves traveling? I want to make a little drawing over here of water waves. And again, you notice that these things are not purely transverse wave. They look more like a combination of transverse and longitudinal. Well, let's say, drew that a little bit too far. Let's say that this person is on a boat, and that boat is here at that time. and it rides up and down on the crest of that wave. He measures the time between those two crests to be 3 seconds. What is that 3 seconds actually representing for this problem from our wave speed stuff? What's that 3 seconds represent? The vision period. So the period of that wave is 3 seconds. Now he measures the distance between the two crests to be 6.5 meters. That's one crest, that's another crest. What is that in wave speed? What is that quantity? That's a wavelength. So from one crest to the next is a wavelength. That's 6.5 meters. If I want to determine the wave speed, it's really not that bad. I'm just going to use this version of that equation. 6.5 meters, that takes 3 seconds. That would be 2.1 meters per second. If I did that math correctly, it could be 2.2. It's 2.2. So that wave speed would be moving at about 2.2 meters per second. Now, the other day I had a tuning fork out just to see if you guys could tell what the 256 hertz tuning fork. There is a model that I can show you of that tuning fork. If I go back to this thing, I'm afraid that it's going to lock my computer up again. But here is a tuning fork that's vibrating. So let's see, vibrational modes of a tuning fork. This is normally how a tuning fork would vibrate. If I hit it lightly, it's going to vibrate in that mode. If I hit it too hard or hit it with a wooden object, I might get a clang mode. That clang mode looks like that. You might recognize that as a different vibrational mode, just like the coupled pendulums were. So different frequency, it's a different kind of mode. You could get into these things that sort of look pretty cool if you watch them for a while, but they could vibrate in any number of modes. What kind of wave do you think this would produce? A transverse wave or a longitudinal wave if it's pushing and pulling on the air like so? Yeah, what do you think?
Longitudinal.
It'd be longitudinal. And so when you look at this wave, when you look at this graph here, this picture, you can see that there are some high pressure regions. This is a period of high pressure, and then here's another period of high pressure. So those particles are pushed together, and that's where that pressure would be high. We tried to measure the speed of sound with our, down in the rotunda area the other day. We didn't do really well, but the accepted temperature for the accepted speed is about 340 meters per second at room temperature. So what I'd like to do is I'd like to determine the wavelength. First of all, it is longitudinal. And it has to do with how that tuning fork is pushing and pulling on the air. The wavelength in air, if I want to find that, I would just go back to my base equation. Velocity is frequency times wavelength. And in this case here, I'm looking for the wavelength, so I'm just going to rearrange that to be velocity divided by frequency, 340 meters per second. It's vibrating at 512 hertz. My calculator gives me 0.664. And I would ask you to see if you can figure out what the units are for that quantity. So let your equation be your guide here and see if you can figure out how that reduces to an appropriate unit for that wavelength. Thank you, Xavier. What are you thinking? Thank you. Hertz. Wait, one more time.
Hertz per meter second.
Hertz per meter second. It's nice try. It's not the right way if you're trying. I appreciate that. What should it be if it's a wavelength? What do you think it should be?
Meters.
It should be meters, right? Let's see how that works out. So again, sometimes we get confused by what these things mean here. So I'm going to write this. Instead of writing it as the hertz, I'm going to write it as a second to the -1, which is really a like seconds to the -1 power. Do you see how that would sort of reduce out? And that would just turn into meters. So 0.664 meters. That would be the wavelength of that particular wave. Okay, Now, I know we have some people that have done some swimming before, maybe, perhaps. Raise your hand. No one? Okay, one person. Nathan, do you actually swim? Like you don't swim for the school, do you, or anything?
I nodded. This
Okay.
is what I trust.
When you're in the water and you're underwater, right? So you go underwater and there's sound in the air around you. Is it possible for the sound wave to travel into the water? Can you hear things underwater that occur out in the air?
Yes.
You can. So a wave that's traveling through air can travel through the interface of air and water. It can. They can travel into it. The question is what I would ask you to say, what happens to the speed of that wave as it goes into the water? Does it increase, decrease, or stay the same, and why? It's really a discussion point. What do you think would happen? Why would it increase? Oh, you said decrease?
Yeah.
It's a liquid, so it's a different state of matter, right? Instead of solids, air, by the way, air is a gas. Particles are really far apart. Travels about 340 meters per second. Sound travels about that speed through the air. If the sound can travel into the water, now that water represents the new medium. Are the particles closer together for water than they are air? A lot closer. Are there stronger forces of connection between one water molecule and the next? I know they're not really solid, but they're able. The speed travels a lot faster through water than it does through air. It's about 5 times faster. And how you know that, or maybe evidence of that, is if you've ever been out in Lake Michigan and you're swimming near the shore, you can't hear the boats that are 2 miles away, but you go underwater, you can hear the engines. And that's because the water travels through that, or the sound travels through that water much more effectively, much more efficiently. It travels about 5 times faster. So the speed of the sound through water is much greater. Now, if that changes, what else changes? If the speed increases, what else changes? If the speed goes up, something else changes. So let's go back to our wave speed equation. If velocity is equal to frequency times wavelength, if I make the velocity bigger because the medium has changed, then something else is going to change as well. The question is what? Which of those things? Is it the frequency that increases, or is it the wavelength that increases? So you might think it's but it's not the frequency. The frequency depends on the source. If it's a 512 hertz tuning fork that's making that sound, that frequency is set as 512. What would change then is the wavelength. The wavelength would become much bigger. And that's because this here depends on that. How far it travels as it repeats itself is dependent on the speed. So if the speed changes, the wavelength will change, not the frequency. The frequency stays the same. Now, I have a demonstration to help you see that, but for purposes of the video recording, I want to finish this slide up, and I'll do that demonstration at the end after the recording is done. This picture here comes from this little simulation. I'm going to show it to you really quick. And so one of the simulators that we would use is a FET wave on a string. And so if you've never seen this before, it's a good animation to sort of show you how circular motion is related to wave motion. So let me get rid of the end here. And let me get rid of any damping, and let's just put this through oscillation, and let me slow that down so you can see it. So the thing on the left is a circular oscillator. We have that bar on there to be able to take just the vertical component of that oscillation, and then that's going to be transmitting as a disturbance along that medium. That picture that you guys have in front of you is a snapshot of this with some rulers there, right? So I can put some rulers on this thing. And then from that, you guys have that in front of you. What I'd like you to do is try to go through and determine for me what the amplitude of that wave is, what the wavelength of that wave is, and if that frequency of oscillation is 2 hertz, what's the speed of that wave? Okay, so try those 3 questions. So if you're watching this from home, you should try those 3 as well. And then the last part of this video will be talking about this equation. Amplitude, were you able to see that from there? It's either 1.6 or 0.8. The most common answer is one of those two. And I'm hoping that you see the amplitude is not the full crest to trough distance. The amplitude is that, which is about 0.8 centimeters. So for that, the amplitude is from equilibrium to maximum displacement. The wavelength, I can move that ruler around anywhere that I wanted to if I had access to those controls, but here there's 2 different things that you can look on that wave to determine the wavelength pretty easily. I would probably go from trough to trough. That's about a little less than 2, that's a little bit more than 5, let's call that 3.2 centimeters. Again, you might not have it that exact, but that would be a place where we could say it's around 3.2. So if that oscillator is going up and down 2 times per second, I should be able to determine the wave speed with just a simple calculation of this. So I take that 2 hertz, I multiply that by 3.2 centimeters, and I get 6.4 centimeters per second, and that would be the wave speed. That's how fast that particle or that wave is traveling. Okay. Now, this last little bit, I don't know if I'm going to be able to do the demonstration I want to do with the springs. If I don't do it today, I'll do it tomorrow. But this last little bit has to do with an equation for the speed of a transverse wave on a string. If you play a musical instrument, a plucked string kind of musical instrument, this equation describes how fast that disturbance propagates. It is very similar to Newton's second law, and I want to show you that from a Newtonian evaluation, Newton's second law serves as a foundation here. A is equal to F over M. If I'm looking at just how forces cause objects to change their motion, I go back to that law, I see that the acceleration of the particles, which is going to, again, be dependent somewhat on how fast that energy can transmit, it is very similar to this equation. The difference is that instead of just a mass, it's a mass per unit length. So people that play the guitar or any kind of stringed instrument, they'll say that they have different linear mass densities for those strings. So a linear mass density is different than a volumetric mass density. Your volumetric mass density might be measured in so many grams per cubic centimeter. It's a mass per unit volume. This is a mass per unit length. So since it's a transverse wave and it's traveling along a string, we're going to look at just what's called the mass per unit length density, and then use that to determine the speed. So for this particular instrument, for them to tune it, they needed to change the tension so that the speed at which the disturbance propagates sets up a wave that oscillates at a certain frequency. We'll study that in more detail with standing waves. If I want to determine the tension, I would go back to this equation. The velocity at which that transverse wave travels is equal to the tension force in that string divided by the mass per unit length. I'm going to square both sides. So when I square both sides, I get that relationship. I'm looking for the tension force, so at this point it just becomes an algebraic manipulation here. The tension force would be equal to V squared multiplied by a mass per unit length quantity. Well, the speed that's needed for us to be able to get that note to be just right is 455 meters per second, so it's traveling pretty fast. Now be careful there, that's not supersonic, because that's not traveling through air. That's the speed traveling through the cord. That's not going to give a shock wave or break the sound barrier. So that's the wave, that's the speed at which the wave is moving through the medium of the string. So I take that and I square it, 455 meters per second, and I'm squaring that. Now I'm going to multiply it by this linear mass density. I'm giving you that mass density in the appropriate unit. The mass is measured in kilograms, the length is in meters. That's important for us to get the right units here. 0.00022 kilograms per 1 meter. My calculator gives me 45.5. What I would like is to see if you can, we only have about 4 minutes. I would like to see if you're able to tell me what the unit should be for that 45.5 by looking at the things on the right. Don't just shout out that you think it's this value. Verify that it is the appropriate unit. I know you know what it should be, right? It should be measured in newtons, correct? Can you verify that that's the case? Let's look at how these units work out. That's a kilogram. I'm squaring meters per second, so that becomes meters squared per second squared. You guys might recognize that as energy. But then I'm dividing that by meters. And when I do that, that becomes kilogram meter per second squared, which is the newton. And so the amount of tension I need in that string to produce that particular node, I can calculate that pretty accurately. If I knew the mass per unit length and I knew what speed I needed, I could do that with that equation. Okay. Guys, that was a lot to have done today. Tomorrow, what I want to do is I want to look at various wave properties, things that waves can do that particles can't. The homework that I put out there for you guys on this is not due tomorrow, but it is imperative that you get that stuff done by Friday so that we can, by Monday, so that we can look at that correctly for Monday, okay?